All right, everybody. So welcome. We are doing the Earth's interior practice. And let's start off with number one. So number one says the inferred temperature and pressure of Earth's interior at a depth of 3,000 kilometers are approximately one. So they're looking for the temperature and the pressure of the Earth's interior. Now, there is a page on the reference table that focuses on the Earth's interior. What page is it, everybody? There we go. We're looking at page 10, the debut of page 10. All right. So we are at a depth. So when we are 3,000 kilometers, right, have a depth of 3,000 kilometers of the inside of the Earth's interior, we need to know the temperature and the pressure. So therefore, when I go to 3,000, right, and I follow, where does it reach my interior temperature? It reaches right at this point right here, and I see 5,000 degrees Celsius. Then when I go to find out the pressure, remember, I'm staying on that 3,000 line, right? And until I hit that black bold line, and when I took to the left, it looks halfway between 1 and 2. So it definitely looks like 1.5 million atmospheres. All right. And so the question that shows that, the answer that shows 5,000 degrees Celsius and 1.5 is definitely going to be, I apologize, choice 3. Here we go. All right, people. Number 2, which graph best supports the range of density in each of Earth's layers? Now, once again, what does that mean, right? When I'm looking at the density of each of the Earth's interior layers. So let me go ahead and take a look at page 10 of the reference tables. And as we see right here, we see the different layers of the Earth. We see the different layers of the Earth, right? And so in this case, the question is just focusing on, I see 4 specific part of the layers that I see. It's talking about the crust, the mantle, the outer core, and the inner core. So let me see if I can find the density for the crust, the mantle, the outer core, and the inner core. Now in the crust, we have the continental crust, which is 2.7, and the oceanic crust, which is 3.0 right here. So we know the crust is going to have this range, all right, between 2.7 and 3.0. Next, we have what is the mantle. And the mantle is going to be 3.4 to 5.6. The outer core density, 9.9 to 12.2. And the inner core, 12.8 to 13.1. So now I'm going to look here and I have to scroll and see which of the numbers that I have that's shaded in is going to be matching up to what I have labeled. All right. First off the jump, I'm already seeing where there are some issues just with the mantle, right? Didn't we say that the mantle was 3.4 to 5.6? Right? So when I'm looking here, the mantle is definitely not 3.4 to 5.6. It stops at 4. It can't be 2. When I look at 3, the mantle right here, it shows me a range of 10 to 12. It can't be 3 because I'm looking just at the mantle. And then number 4, I do see 3 point, no, I actually don't. 3.4 to 5.6, the bar that's shaded in here, it definitely looks to be, let's say, 4.5 to somewhere, it looks like 6 point, let's just estimate 6.5. But we know, as we said right here, the mantle is just supposed to be 3.4 to 5.6. So 4 definitely cannot be. And so that's why the correct answer is choice 1. And if you were to match up all your numbers with the layers, with the correct density layers, you would see that it is correct. All right, number 3. So number 3 says, base your answer to the following question on the diagram below, which represents zones of Earth's interior. Zones of Earth's interior identified by letters A through E. And there you go. The scale shows depths below Earth's surface measured in kilometers. Now the question says, which zone of Earth's interior has a density closest to the densities of the other terrestrial planets? All right. So we first got to start off and identify what is a terrestrial planet again. All right. Well, my terrestrial planets are the first 4 planets of the solar system, which are Mercury, Venus, Earth, and Mars. Come on up. You are the next contestant to be a terrestrial planet. All right. So as we are looking, we see my first 4 planets of the solar system. These are my terrestrial planets. And I have to take a look at their densities, right? So Mercury has a density of 5.4, Venus has a density of 5.2, Earth has a density of 5.5, and Mars has a density of 3.9. So I know all of their density ranges from 3.9 to 5.5. All right, let's keep that in mind. 3.5 grams per cubic centimeters to 5.5. All right. Now, with that being said, 3.9 to 5.5, keep that in mind. All right. Those are the densities of the terrestrial planets. Now, I have to find, as the question says, which has a density closest, which zone of the Earth's interior has a density closest to the density of the other terrestrial planets. All right. And so when I'm looking on page 10 of the reference tables, right, to see the different zones of the Earth's interior, I scroll and I scroll and I scroll. And let's see. Do you remember what my numbers were, right, for the terrestrial planets? Remember, my numbers were that 3.9 grams over cubic centimeter, right, to 5.5. Those were all the ranges. Those are all the ranges of the terrestrial planet. Now, which zone would these numbers fit? You got it. This zone right here, which is also known as our stiffer mantle, right? So now when I need to know the depths of this zone, right? The stiffer mantle is what would fit the densities of the terrestrial planet. I need to find out what are their depths range. So when I scroll down, let me continue to scroll down. I know my line is not perfect, but we gonna make it. All right. And when I scroll down, all right. So this zone right here is definitely somewhere around, it looks like I'm gonna get estimate about 700 kilometers, right? And it doesn't cross 3,000. It's like right next to 3,000. So let's just say 2,900 kilometers, right? And this number is going to help me to determine where the zone is. All right. So now when I'm looking, the zone letter that has around 700 kilometers to close to 3,000 definitely looks like zone C. And so therefore, my correct answer is zone C. All right, number 4. Number 4 says the inferred temperature at the interface between the stiffer mantle, right? Let me box that. And the asthenosphere is closest to what? And we're looking for the inferred temperature at the interface, right? At the interface, another word for interface, you could even say the boundary. So what page am I going to look at, everybody? Boom, you know it, page 10. All right. And so I'm going to look at the interface, right? That boundary that is between, as the question says, the stiffer mantle and the asthenosphere. All right. So the stiffer mantle is here. The asthenosphere is here. Oops. And I need to follow this boundary line between them. All right, I'm going to try and be as accurate as I can. All right, you see this purple line I'm drawing? And I'm just going to follow this line all the way down until it hits the, oh, my nose is horrible, until it reaches the inferred temperature. Now take a look. The interior temperature is this black bold line right here, and it stops at this point of the interface. And when I take a look, it definitely looks kind of halfway between 2000 and 3000 degrees Celsius. And so because it looks like, I'm just going to say kind of halfway, right? I would say 2500 degrees Celsius. Now, when I look, what answer is closest to that? And it definitely looks like answer number 2. Boom. Base your answers to questions 5 and 6 on the cross section below, which shows the boundary between two lithospheric plates. Point X is a location in the continental lithosphere. The depth below Earth's surface is labeled in kilometers. So I see the diagram. Point X is right here. And it says point X is located in which Earth's layer? Now we know that point X, as they said, is located is a location in the continental lithosphere. And when I take the estimate, right, it's definitely no more than 100 kilometers. Keep that in mind. So point X is definitely has a depth of less than 100 kilometers. So what page of the reference table am I looking at, people? Here we go, here we go. We're looking at page 10, our new favorite page of the reference tables. All right, and so I'm gonna look at my depth. Well, number one, first off, what if I even look at my depth? Point X is in the lithosphere, correct? We saw that in the reading. And what are the two locations, right? Parts of the Earth's interior that's part of the lithosphere. We have the crust and the rigid mantle. So that already gives us an idea, all right? And I also know, if you take a look, right? We know that it definitely has to be less than 100, right? And we also know, you see this boundary line right here? This is the, let me see, sorry. So this represents the borderline of the lithosphere, right? And so that's why it's definitely going to be somewhere within the crust, right? Or the rigid mantle. And when I'm looking at my answer for point X, the best answer is definitely the rigid mantle. Now, number 6 says the temperature of the asthenosphere at the depth where melting first occurs is inferred to be approximately what? So I'm definitely going to be looking at the temperature of the asthenosphere, and we're looking the temperature of the at the depth where melting first occurs is inferred to be where. So when I look at my reference tables, right, I'm at the asthenosphere, which means that I'm going to be looking in this shade, this gray shaded area, right here. So let me highlight that. There we go. And I'm going to look where melting, the depth where melting first occurs in the asthenosphere. All right. What I'm going to do is I'm going to continue to keep highlighted the asthenosphere later as I'm scrolling down. All right. As I'm scrolling down. So this yellow category represents the asthenosphere. All right. Do we see where it follows? All right. And I'm looking for the temperature where melting first occurs. So when I'm looking, the melting first occurs in the asthenosphere. It definitely looks like, and I'm going to zoom in a little bit more, where melting first occurs somewhere around here. You see the dashed lines where you see melting point? All right, so it says where it first occurs. So temperature is definitely around here, which is a little above 1,000 degrees Celsius. So when I'm looking, the option that shows a little above 1,000 degrees Celsius is definitely going to be choice 2. All right, number 7. The diagram below shows the cutaway views of the inferred interior layers of the planet Mercury and Venus. All right. What is the reason for the development of the interior layers of these two planets? Now, one thing I know, right? I see the mantle and I see the core, right? A nickel iron. And when I look at the Earth's interior on what page, everybody? Page 10. One thing that I find different is for each layer of the Earth's interior, I see a different density, right? And one of the things that I'm also seeing is that the higher the density, then I know the more towards the center that the materials are going to be, right? It's kind of like if you remember we did the liquid lab, right? And in this liquid density lab, we would pour different substances, and one of the things we found out is that when we pour the different substances, right, we know because of gravity, right? Gravity will pull everything to the bottom. And we notice that the substance that has the higher density is going to sink to the bottom. The substance that has the lowest density is going to rise to the top. And so, because of density, we saw a separation, right, of the different layers of the different liquids in the when we did the liquid density lab. So, in the same sense that we see here, and we're seeing that for each layer of the Earth, we are also seeing different densities. So that lets me know that densities play a role in separating the core and the different layers of planets. And we know that gravity wants to pull everything to the center, right? And so by coming to the conclusion of these two realizations, we can conclude that my correct answer is going to be choice 3, because we know that the reason why we have the development of those interior layers for these two planets, right? The reason why the mantle and the core is separated, right? And the reason why the core is in the center and the mantle is not, is because of the different densities that these materials have. And so that's why the correct answer is choice 3. All right, people, let's take a look at number 8. Which combination of temperature and pressure is inferred to occur within Earth's stiffer mantle? All right, I love these types of questions because we could almost try it out, right? We could almost try it out to see which one is going to fit within the Earth's stiffer mantle. So it looks like we're going right back to what page, everybody? Page 10, right? And we know page 10 focuses on the inferred properties of Earth's interior. All right. And so what we can do is pretty much let's do a trial, almost like a trial and error thing, pretty much, right? We can test out the different numbers and see what we get. All right. So the first combination we're going to try very quickly is 3,500 degrees Celsius and 0.4 million atmosphere. So let's try that out real quick. Let me zoom this out. All right. So 3,500, right? So it looks right around here, 3,500. Oops. Here we go. 3,500 is here, right where the black line is. So we label it here. Let's label this A. And 0.4, we know it's a little less than halfway. And so we'll label it right here. That is A. All right, let's keep going. 3,502 degrees, so 3,500 degrees Celsius and 2 million atmosphere. So we're going to test this one out now. All right, and let's see. So 3,500, let's do this a different color. Let's do red. 3,500 degrees Celsius is right here. So I'm gonna put A comma C. All right. And it says 2 million atmosphere for the pressure, and it looks like it's gonna be labeled right here. I should label this actually B. Yep, let me label this B. Okay. All right, so we're gonna keep that in mind. Now, number 3, 5,500 and 0.4 million atmosphere. All right, so therefore we're gonna label this C. Let's do a different color for C. I'm thinking green. So 5,500 degrees, right? And we're looking at the interior temperature. So we stop at the black bold line. I'm gonna label this C. And 0.4 is right here. Oops, sorry. All right, and so A and C are in the same place. And then last, we're gonna do 5,500 degrees Celsius and 2 million atmospheres. And so 50, let's color this brown, okay? 5,500 degrees Celsius right here, right? So it's the same as C, and I'm gonna write D. And what did it say? 2 million atmospheres. So B and D. All right. Now, the layer that we're looking for is the Earth's stiffer mantle, right? And so what I'm going to do is I'm going to scroll up and I'm going to highlight the stiffer mantle. And wherever I see both options, right? A, B, C, or D, wherever I see both options, that's where they're going to tell me. That's where I'm going to find the answer. So the stiffer mantle is here, and I'm going to see what points do we see. Remember, we're looking for which option has both the pressure and the temperature correct at the stiffer mantle. Now, I shaded in yellow because if you look up what I shaded, you'll actually see that this connects with the stiffer mantle. And so when I look, the only one, right, the only option that has both letters for pressure and for temperature is choice A. See? Choice A, right? All the other letters has one letter in and another letter out. And so my correct answer is going to be choice A, which is 3,500 degrees Celsius and 0.4 atmosphere. All right, guys. So number 9, we are almost there. What happens to the density? What happens to the density and temperature of the rock within Earth's interior as depth increases? As the depth increases. All right. So what that means is when I'm looking at the reference table, let me just clear all this up real quick. All right, there we go. I apologize. All right. Okay. So what they're saying is as the depth increases, right? As I go from zero, from a depth of zero all the way to 6,000, two things I need to know is what happens to my temperature and what happens to my density. All right. So number one, as I'm looking, when I go from 0 to 6,000, right, of a depth, I'm looking at the interior temperature, and look what happens. As I go from 0 to 6,000 kilometers, the depth, right, temperature, the black line for temperature looks to be going up. It looks to be going up. So that means for temperature is definitely increasing. All right. Now I got to look to see, well, what happens with density, right? And so remember, if I follow this same number chart, right? 0 is located right here, and 6,000 is right here. Well, technically, we'll be going greater than 6,000 kilometers, right? So that means my 0 mark would be here, right? And my 6,000 line would be somewhere right here, right? For kilometers. And what happens to density? Well, as I'm looking, right, at the very beginning, we started off with 2.7. At the very beginning, we started off with 2.7. And when I'm in the inner core right here, look at the density range, 12.8 to 13.1. So the fact that I started at 2.7 and it looks like the numbers increase as I get deeper, deep in the Earth's center, that means that density also increases. What that leaves me with, everybody, choice number 3. All right, number 10. So number 10 says there we go. Which temperature is inferred to exist in Earth's plastic mantle? So we got to find which temperature is inferred to exist in the plastic mantle. So I'm going to go to page 11. I'm sorry, page 10. Oops, made a mistake. I'm only human, right? And we're going to go to the plastic mantle, the plastic mantle. It's so important that we don't confuse that with the stiffer mantle, right? So the plastic mantle is this gray area, and what I'm going to do is I'm just going to highlight it so that way we do not make any confusion as to what we're looking at. And as I scroll down, all right, I'm going to, oops, there we go. Let's keep going. And remember, we are only focusing with temperature. We are only focusing with temperature. All right. Oops, sorry. There we go. All right. So when I'm looking at the plastic mantle, right, that's what's highlighted in yellow. This column right here is a plastic mantle. And I'm looking, right? So the minimum temperature that I see right here, right? Because I'm looking at the interior temperature. The minimum temperature looks definitely to be a little over 1,000. So let me give an estimate, and let's say like 1,100 degrees Celsius, right? That's what it looks at that point. And then the maximum temperature of the plastic mantle at this point, we would say what? Would you say, let's say 2,600 degrees Celsius, just to put it on the safe side. So that means I need to find a number, right, that is between 1,100 and 2,600 degrees Celsius, right, of a temperature that would be within this yellow column which represents the plastic mantle. Look what happens when I scroll up, right? Focusing on the plastic mantle that I highlighted in yellow. And so the best option would end up being choice 1, 2000, right? 2000 definitely degrees Celsius has a temperature definitely within the plastic mantle. If you take a look at the other temperatures for yourself, I won't do for all of them, but let's say we took a look at 3000, for example. If you look at 3000, 3000 is located right here. Let me use a different color. All right. And 3000 located right here. And it is outside of the plastic mantle, right? It's not in the yellow highlighted category. So that's why 2000 would be your best answer. All right. That is all that we have. Have a wonderful, blessed day. Please make sure to like, share, and subscribe. Until next time, peace.